Hello and welcome to part 2 of lecture 19 covering rotational kinetic energy, where we're going to do a couple of examples, starting with a conceptual question. So in this conceptual question, you can see there's two parts, A and B, and the whole idea here is to illustrate the difference between what's called a simple pendulum and a physical pendulum. So let's read part A. So we want to show that conservation of translational energy and conservation of rotational energy give the same results, or at least the same resulting final velocity, for a simple pendulum as shown, released from rest from a given height. All right, so let's define our system. So here, since we're going to use energy, this is our point 1 and our point 2. And for a simple pendulum, the moment of inertia is given by ml squared. Okay, notice that's the same moment of inertia of a hoop. More on that in the next lecture. It basically just means that all the mass is all the way out at the end. Okay, so how are we going to approach this? Well, we want to start by considering energy 1 and energy 2 using conservation of mechanical energy. And we're just going to use translational energy. So given translational energy, we have an mgh and a 1/2 mv squared, which gives us a final velocity of the square root of 2gh. Now we've done this before. We've used conservation of translational energy for pendulums, but they were always simple pendulums. We were always making the assumption that all the mass was right here and that the mass was a particle. Okay, didn't have diameter or length or radius or anything. Okay, but what if we use the appropriate moment of inertia, its rotational mass, considering that it is a rotational system, but one with basically a rod or a string of negligible mass? In that case, mechanical energy E1 equals E2 becomes, in a rotational sense, mgh equals 1/2 I omega squared. Why is that? Well, because our pendulum is not translating. Its center of mass would be right here, and certainly that center of mass is not moving in any translational sense, no x, y, z movement. So this is our whole system, okay? And then the I becomes simply ml squared, because it's a simple pendulum with all of its mass a full radius away from the center of rotation. And omega, by definition, is v over L, because there's no slipping here. It's not even an appropriate problem to consider slipping. Translation is coupled, to use a technical term, with rotation. And look at the result, square root of 2gh. Well, that's good, because that tells us that everything we're doing before, we were kind of not mentioning rotation, treating our simple pendulums as particles, and then using translational kinetic energy to get answers was right. That's good, okay? So we were allowed to do that. We didn't exactly know why we were allowed to do that, but now we see, okay? Or we're starting to see. But, here's the big but. Now what if we talk about a pendulum that is an object, that isn't a particle, that has a different moment of inertia? So here, we're going to show that something called a physical pendulum with the same mass, just generally m, and a moment of inertia of 1/3 ml squared. Again, you'll soon see where that comes from. And it's pivoting about a point shown, and the point is considered to be close enough to the end that it's effectively at one end. And it's released from a height h, okay? Then we want to show that the resulting final velocity can only be found with conservation rotational energy. In other words, if we try to use translational energy naively, we get the wrong answer. Okay, so we want to define h. All right, h represents the change in height of the center of mass, because that's the only thing that we can discuss here meaningfully, is the center of mass is changing. The overall length is L, that's just shown here. Okay, and again, we can't, if we're going to use a potential energy term, if we're going to use a height in our potential energy terms with our conservation of energy, it can't be any other height. I mean, case in point, what if we use the height difference of the tip of our physical pendulum, the very end, the point furthest from the pivot? That'd be a totally different number, right? Because when it swings down, it's gonna be a bigger distance, right? H for the tip is actually larger than H for the center. And if you don't believe me, or if that's kind of hard, maybe you kind of feel like that's right, well, think about what's the height difference for the pivot itself. 0, you know? So the height difference varies as we move down along our physical pendulum. So it absolutely matters what point we choose. And the only point that physically makes sense, because the only point where gravitational force acts is the center, okay? Now, our rod is uniform, so the center is the geometric center as well, but need not always be the case, okay? I keep mentioning that, but we'll see that. All right, so moving on. So we're going to use conservation of energy. mgh becomes 1/2 I omega squared. Okay, I'm using rotational energy because I want to show it only works with rotational energy, so I'm going to start with rotational energy. Then we're going to go ahead and insert our correct moment of inertia, which was given to us. We'll solve for it later using calculus. And then we're going to replace omega with v over L. And then I'm going to go ahead and solve for our final velocity. Okay? So you can see that in this case, right, we get a different value. All right? So because our rod is uniform, L equals 1/2 L. Okay? And little l is 1/2 of the big length. So what I'm referring to here is, so this result, all right, this L, little l times big L, that comes from the center of mass. And so then when we solve for our final result, we get the square root of 2/3 times GH com. And if we'd used translational energy, we of course would have gotten the same result as for the physical pendulum, the square root of 2GH, which would have been the wrong answer. So we can see, in fact, the translational energy for the physical pendulum is smaller. Instead of 2, it's 3/2. That's the same kind of result we saw comparing the rolling sphere, the rolling hoop, the rolling shell to the sliding block. They're all slower. They're all translationally slower because they had to give some of their energy to rotation. Same here. This physical pendulum has to actually move that mass, right? And all the mass isn't at the end. Instead, it's distributed throughout it, okay? And so we get a smaller result for that translational energy because it's not just translating, it's rotating as well, okay? And just to be clear on the terms here, because I don't want there to be any confusion. So, okay, so we have so L represents the overall length. L is given as, I'm saying that L is 1/2 of the overall length. So I'll fix that in just a second. And so then when we do it, let's see, so H com, I leave H com in the result. Okay, yeah, so this right here, this V over L, that's because here is the translational velocity of the center of mass. L is the distance from the pivot to the center of mass. Okay, so L again is just this distance. Even though in the figure it looks like I'm calling L the overall distance, I'm actually not. I'm saying that the overall distance is big L, although this looks like kind of just chicken scratch or maybe an arrow or something. This big L is actually referring to this overall vector here, and then little l is this dotted line. Okay? All right, good. All right, so we'll come back to example 3, but I want to show you one other example. I'm going to leave these ones for practice, 4 and 5 that is. These will be available for participation points before I eventually upload the solutions if no one chooses to present them. This is a good one, reflection 1 and example 6, which go together. You can see the approach that a student took where they made a mistake, they left some things out, and then you can correct that in your own solution here. Okay, but this is example 7. This is one I do want to show you. Okay, so what's going on here? So a hollow sphere with a moment of inertia of 2/3 mr squared. That's the same sphere we saw before. Okay, and that's true of any uniform hollow sphere. That moment of inertia is true. And we're given its mass and we're given its radius. Turns out its mass will cancel out. And it's going to roll without slipping into a bowl as shown. The bowl has friction on the left side and no friction on the right side. Okay, so over here where it's shown to be bumpy, that's where the friction is. Over here where it's totally smooth, that's the no friction part. Okay. Thus the sphere suddenly stops rolling and starts sliding at point Q. Okay, so at that point it actually becomes a purely translational system. Up from P to Q, it's a rotational and translational system. From Q to R, it's a purely translational system. Okay, it has a release height of 1 meter, and then how far up the side will the ball slide? Okay, so let's find this. So we're going to first use conservation of energy go from P to Q. And then use conservation energy go from Q to E max, which is some point up here, right? It's maximum height that it reaches. So what does that look like? Okay, well, initially it only has gravitational energy, and that's relative to its center, which is right at H, okay? And then it's going to roll down. When it rolls down without slipping, it's going to have both forms of translational energy, of kinetic energy. It's going to have a translational form of kinetic energy and a rotational form of kinetic energy. The translational form of kinetic energy refers to the velocity of its center of mass, which would just be its center. And it's also going to have leftover gravitational energy because it doesn't have a negligible radius. Its radius is 1/10 the release height. It's actually never going to get to the bottom, and so it's not going to be able to use up all of its gravitational energy. Okay. In other words, I mean, we could have in a sense set its gravitational energy as there because that's the lowest it ever gets. At least it's the lowest its center ever gets. But we didn't. We set it up this way, and that's fine. It's a perfectly valid choice of coordinate systems. Okay. So that means that its center of mass has a velocity that is equal to 6/5, or the square root of 6/5 times g times h minus r. Okay? And that comes out of doing our typical substitutions that we've seen a couple times now, right? Replacing omega with v comm over r, replacing I with the given moment of inertia formula, and then just simplifying everything, combining like terms, and then getting our velocity of center mass. Okay? And then we're going to use that velocity of center mass to find out how high it goes. So now we're going to equate EQ to E max. Right, again, E max is going to be somewhere up here. All right, so that then just becomes translational energy and then equal to mgy max, okay? And let's see, I should have, looks like I'm missing the leftover kinetic energy because it's, or potential energy, because it should have that potential energy, okay? So, yeah, because I should have 1/2 m v comm squared plus mgr because it does still have potential energy. So that will show up there, which is why, let's think, because then we have mgr. Okay, so I'll need to fix that. So let me go through and then I'll fix these numbers because it should be slightly different. It should be 3/5 times h, not 3/5 times h minus r. Okay, but let me first show you the other approach, and then we can fix that small mistake. Okay, so the point is that it's not going to get as high. Okay, why is that? Well, because when it reaches the bottom and it stops rotating, it's now that rotational energy isn't able to become gravitational energy again because it's just trapped, right? That rotational energy on the way back up, once the ball just starts sliding up without rotating, it can't do anything. It can't turn back into the gravitational potential. It's just going to stay there as gravitational potential relative to its own center of mass. Essentially, it's able to tip, but it has the capability of tipping, but it won't because it's sliding without rotating. Okay? On the flip side, if we consider part B, where it says, what if the sphere was released from the same height but at point R? How high will it go? Well, in this case, it's going to translate down without rotation. Then it's going to start rolling on the way up, where it's going to have both translation and rotation. So then it's actually going to gain energy on the way up. What does that look like? Okay, so same sort of approach, except our first relating ER to EQ is just the same as it would be for a sliding block. So we get a very simple result of just 2g times h minus r. Then we're going to relate the energy at Q, the purely translational energy. Well, actually not, because there's still leftover potential energy. We're going to relate that to E max. Okay, now we have a rotational term. We're going to combine our terms, and we end up with 5/3. So it actually goes higher up. Okay, now let me fix the mistake before I make my final point here. So this mistake showed up twice. Okay, so here we should have, I was looking over this, but I didn't catch it until I started presenting it. So I have 1/2 m, it should be mgh, mgr, because that's how much gravitational potential energy is left. And so then when we combine our terms here, we're going to have, I'm going to replace this with the 1/2, the 6/5, and so on. And then we'll have our other term over here. This is where we'll have our plus mgr. And that should cancel out then. Let's see. So I should end up with, so 1/2, 6/5. So it should just be 3/5 r. I'm going to check that. Let's see about what our terms become. Okay, so 1/2 times 6/5, and then plus 1. Okay, or negative. Okay. All right, so that should be 0.4. It gets down there, but it's still got gravitational potential energy. And this this m would have canceled here. So this would just be GR. So plus GR, because it does, that's the leftover potential energy. Let's just do a final pass here. So it seems like it should just give me 3/5 H, because I have that much leftover kinetic energy, and I'm going back up. Honestly, though, I should just be able to cancel them out, right? Because it didn't go all the way to the bottom, so it didn't pick up as much kinetic energy. But then, let's see, then it's going back on its way up. Okay. So then we have our GR term. So if I plug in everything, what do I get then? If I just plug in 1/2 times, and I'm just doing this part over here, so 1/2 times 6/5 times 1 minus 0.1, and then plus, and the G would have canceled here, plus 0.1, then I get 0.64. Let's see, 3/5 times 1 is 0.6. Okay, so I guess it's plus R then, because, yeah, so it ends up being exactly, let's see, so if I take 3/5 times 1 plus 0.1, that's 0.66. Okay, so here, I'll write it this way then. All right. And then, so this would just be plus R, like so. All right, and then, so that's going to give me, is that right? Well, yeah, it is. I mean, that's exactly what I have. And so that's going to give me 0.64. Yep, 0.64, okay. So there we go. Okay, but doesn't make up as high. And then over here, we'll have the same sort of thing. Let me fix it here as well. All right. And then I'll have plus MGH, RMGR, and we'll cancel out the M at this stage. And then in the next one, this is where we'll have I have to clear it up a bit, so I'll just put the plus R on each of these. So let's do that over here, try to make space for them. All right. Okay, so plus R, plus R, plus R, and then I'll show that G cancels out in this stage as well. All right. Okay. Well, actually, here it should cancel out. So here, it should be, let's show it correctly. Okay, so here will be plus GR, plus GR, and then over here, this is where we're going to cancel it. So this is where we'd have, for dividing, Okay, all right, that works. All right, and so then it should just be 1.6. That's the final answer. And I know I had to do that a little quick and dirty, but that'll work. Okay. And again, it was just a small mistake. Okay, but the important part, the important takeaway is that when we release it at point R, right, when we release it up here, it's actually going to come down and it's going to go up higher. In this case, it would kind of fall out of the ramp, right? Because it actually gains energy in a sense once it starts to rotate. You might be like, well, where's that energy coming from? You can't just get energy from nowhere. Well, that's the whole thing, right? The ball had the capability of tipping over. But if it continues to translate of rotation, then that potential energy, that gravitational potential energy relative to its own radius, is never getting used. But once it starts to roll, when it reaches this stage, now that potential energy actually does start to become kinetic energy, which allows it to become a greater potential energy for the total center. So that's where the extra energy comes from. Okay? All right. So we'll actually wrap it up here because I need to move over to the